Okay, welcome to Privacypass at IETF 114. Thanks for joining us. Just real quick, here's the note well. I think you're probably well acquainted with this, but if you need a refresher, you can take a quick look at this reminder. A couple of reminders for this meeting is it's really helpful to join the meeting with the on-site tool so you can join the queue, and so you can so we record your attendance as well. So please join the on-site meeting queue. Also, please wear your mask except when speaking. I think that's the main things. Main thing I want to do right now in terms of administrative trivia is to get a note taker. Can somebody please volunteer to take some notes for us? Be really helpful. Let us get us through our agenda. We do need a note taker. Going once. Thank you. What's your name? Marcus. Thank you. So we have a pretty full agenda today. So with initial discussion about deployment experience, status of the core documents, talk about rate limited token, and then key consistency and discovery. Are there any additions, modifications to this agenda that anybody would like to make? Okay, then I think we can jump in. Did you have a?
I want to note that we have a full agenda for our very short session. So I will be running a timer to include both presentation and questions on each topic.
Can I?
Oh, yeah, you can. If you, yeah, why don't you do that? Yeah.
You just
Yeah.
you can let me do it. All right. Hi, everyone.
You have to click it on.
Oh.
Thank you.
Hi, everyone. That's loud. I'm Tommy Pauly from Apple, one of the co-authors on some of the documents we have here, and I'll be presenting some of our current status on implementation and deployment testing here for Privacypass. So first, I wanted to point to some implementations. This is of the base specs. So this is the token issuance and authentication scheme to request and redeem tokens. There are a couple different open source implementations if you want to try these out. There's one that is written in Go that Cloudflare has that implements client, origin, attester, issuer, either as one thing or as separate things. And you can use it for all the basic variants, and you can also test out the rate limited variant. So this is a very useful tool for doing interop. There's also a new one coming up from Raphael that does client, origin, and issuer for the basic variants. So if you're interested in building stuff, these are good resources to interop with. But beyond that, we are also doing some non-open source implementations and actually getting some deployment experience. At Apple's developer conference in June, we announced that we want to replace CAPTCHAs with private access tokens, which is really just Privacypass, but that's what people wanted to call it for branding reasons. So it is just Privacypass doing the basic type 2 publicly verifiable tokens. And so we introduced a broader developer community to this concept and pointed back to Privacypass. they wanted to get more engaged. So hopefully that will kick up some interest, and I've already seen people looking at this a little bit more. So yeah, we're trying to increase awareness. We are allowing developers of apps to be able to do token issuance and redemption, as well as anything that's running within WebKit environments on iOS and macOS will automatically be able to support this now. And so we have attestation and token issuance that we're working with to try to kind of get some tests going on in this ecosystem. But the goal is to have it grow and to have, other attestation work. And I look forward to seeing some of the previous Privacypass browser extensions, et cetera, be updated to be compatible with the current specs. For the tests that you can do with what we have on iOS and macOS, currently Cloudflare and Fastly have both deployed token issuers that are specifically for this initial demo experimentation phase. These are the two issuer names. You can find more information about them. For our devices, we are doing some attestation with an iCloud server that is doing device and account attestation, but other platforms and other browsers and applications can do other types of attestation that could work with these issuers just as well. iOS 16 and macOS Ventura are currently in beta, and they support all the client functionality automatically. If you want to explicitly test this out, if you have one of these devices that's on these builds, there are some demo origins like this Cloudflare one, which will just always say, I'm going to give you a CAPTCHA unless you can show me a token. But also in the wild, there are deployments that are actually starting to use this and try it out in non-forced cases. Before I get into that, just what is supported here on our client, this is only doing type 2, and I believe that's also the case for the issuers, that they are doing the publicly verifiable basic token types that are using RSA blind signatures. For our client, we are doing a split origin attester and issuer model, and our client supports either specific origin or cross-origin tokens. And there are some limitations around what we'll do in the web context. We will only accept token challenges and redeem tokens to things that are first-party domains within a web context, so that random ads and other stuff can't start trying to poke and get tokens out of you. Cloudflare managed CAPTCHAs is one of the things that's already doing requests for tokens. And so currently right now with these beta builds, we're seeing 35,000 tokens being issued per day, and 16,000 tokens that are being redeemed, so that you're seeing kind of like the client fetching batches and not necessarily spending them all, but then we're actually spending them later to say, okay, get around this CAPTCHA because I've already done the attestation. And I don't have detailed latency information, but it's all very, very minimal. It's not really impacting any user-facing things so far. So I believe that's it for these slides. I guess if there are any questions about the specific implementations, let me know. There are links to the open source repositories if you want to play with those too. So please try it out. Do interoperability testing if you want. All right. Seems like there are no questions, so we can probably move on. Do you have anything? Oh, you are. Oh, Nick. Oh, sorry, I didn't see it. Hey, Nick.
Nick Doty, CDC. Thanks for both translating and giving us some implementation experience. I'm curious whether, well, I have lots of questions, but I'll just ask one. I'm curious whether we've considered the problem of over-reliance, that that some developer might just say, hey, I hear Apple can attest to all the devices. Therefore, I'm just going to block access permanently to anyone who doesn't get one of these tokens. and whether we've considered sort of either protocol or implementation changes that would withhold a certain small percentage of the time to encourage the developer to realize, oh, I can't get this 100% of the time.
That's a very, very good point. So we absolutely don't want reliance like that. In our communication publicly, we were like, do not do, I mean, you should only do this if in lieu of a CAPTCHA, and you always need to fall back. But of course, advice does not give you everything. One of the nice things is that it will not happen all the time, and I didn't go into those details, but this may be something we want to add advice to in the documents, probably I think in the architecture document that's talking about the whole ecosystem. So first, there's actually a human level toggle where some users can disable this, but beyond that, our attestation system will rate limit you, but even on the device, we have limits of when we are willing to get a token or not. So we will not randomly, but if we see more than a couple token requests in a minute or based on what process you're in, we will just ignore some requests. So you certainly would not be able to do a site that did 100% and have it work. But I agree that this is something that we should talk about more. And I think having something randomly not do it some percentage of the time may be one mitigation for this. All right.
Okay, thank you, Tommy.
Cool. And I think next is the base drafts.
Yep.
And I think I'm going to present that, and then Chris will talk remotely about the rate limited.
Perfect.
Yeah, unfortunately, a lot of the authors have conflicts or in mid-travel right now. So. All right, I am still Tommy Polly, but now I am speaking on behalf of more co-authors, Chris Wood and John Iyengar, Stephen Valdez, amongst others. So we have 3 base drafts here. We have the architecture, which essentially describes the different models for using Privacypass and deploying Privacypass. We have the authentication scheme, which is how an origin can request tokens and clients can redeem tokens. And we have the protocol, which defines 2 flavors of token issuance, one that is privately verifiable and one that is publicly verifiable. So this is just a slide to go into some of the recent changes. Overall, the authors think that these are pretty mature. From like a technical interop standpoint, we think they're done and would like to get those moved along, but I think there are things around wording that we still need a bit of work on, but we hope to consider a last call soonish. Some of the recent changes include for architecture, clarifying the trust model, removing some old text that no longer really applied around parameterization, and adding a bit more text to talk about centralization, although I know there are other documents proposed that will go into more depth there. For the auth scheme, based on the discussions at previous meetings, clarifications around how to support multiple origin names being related to a given token were added. We added guidance around how to handle and process token challenges, clarified what you needed to do in order to prevent double spending, depending on what type of token context was being added. And we also added test vectors so you can confirm your implementations. And for the basic issuance, very little changed. There were a couple of things really to clarify fully how the token verification worked. Some of it was just more implicitly saying, oh, you know how blind RSA works, but we tried to make it a little bit more clear. And we also talked about how you get the token validation keys from a consistent location. So just the couple open issues we have that I wanted to bring up today. One is actually just based on an early IANA review. IANA has been doing a great thing of actually, before we go through the full process, they are reviewing all of the working group documents that have IANA considerations in them that are being presented. So thank you, IANA, for doing that. So the auth scheme document defines a registry of token types, and the basic protocol issuance defines two types in there, a privately verifiable and a publicly verifiable token. And the auth scheme also reserves some types to be able to do greasing of making sure that you can accept unknown types within your auth challenges and redemption. IANA did have a couple questions. We were not clear where this new registry should live. They assumed it would probably be on a new Privacypass specific page. I think that makes sense. So the document now says that. I would like to hear if anyone disagrees with that, or what we should call it. That's very much a bike shed. And then the other thing is, what do we want the review policy to be for new entries into this? What we put in for now in the PR is specification required. And so that would involve designating experts and then requiring that you have a stable spec in order to allocate this. I don't have particularly strong opinions. This seemed like the right thing for entirely new token types, because you have to have a pretty full specification to be able to implement against it. But I would love to hear opinions of the working group. If they can find their in-queuing buttons. Chris would.
Yeah, this seems fine. I don't know if we need to say anything more about the type of like analysis that goes into a token type before it actually winds its way in the registry. Like HPKey, for comparison, like establishes a registry for like different algorithms, and it just says if you want to be on this list, you need to like meet certain properties, like certain security properties. We could say the same exact thing here, and then require that the documents like demonstrate in some way, I don't know what that looks like, that they actually meet the properties, but provided that that's done, I think that this is a reasonable way forward. And provided that the experts who can assess it are able to reason about the correctness of those properties.
Right. I don't have the text in front of me right now that I proposed, but I think there is a sentence there that is recommending what the experts review. And I think it says something along the lines of like, it needs to meet the properties, but I think that's the interesting sentence to make sure is correct, that that's the right advice to the experts.
Yeah, cool.
Thank you.
Hey, David Skenazy, quick Varant enthusiast. How is this encoded?
These are not varants. This is, I think, a 16-bit field, because having a dependency on varants here isn't really necessary, and that's a lot of token types.
All right, just the really nice thing about those is even though you have 2 to the 62, we'll only ever use 10. But what it means is that you can like do whatever you want for experimentation, and it makes life a lot easier. So you don't have to do specification required and let people do. I try to push back on specification required for the entire space, because it encourages people to just skip IANA altogether and squat on values if they don't want to have a publicly accessible spec.
So you're talking about essentially the approach of reserving some experimental values that can never be allocated?
No, so I
Or-
mean, MT would make this argument better than I can, but that wasn't a great success in TLS.
Right.
So rather having somewhere where you can just have like, what's the term? Not temporary, but provisional.
Yeah, provisional allocations, I think that's fine. And that, I think, is compatible with specification required, as far as I understand. Like, you can ask for a provisional, and then you can always then say, nope, we changed it. We
I
unadopted
guess what
it.
I'm saying is try to make this a bit more like the quick one. You don't have to go full Varant, even though I'd love that, but saying some of the space is specification required, and some of the space you can do provisional. But provisional, the IETF IANA reserves the right to yank it from you at any time. And
Okay.
that way you avoid all these problems, and that's been working really well for us.
That's a good clarification just to make in the IANA notes. Okay. Alrighty. If we have no other thoughts on that, then I'll move on. Oh. The other issue, number 141, is it was more of a kind of architectural question about what does the ecosystem do if the attestation service, which could be the issuance service as well, stops doing the right thing. So like it just says, it starts giving out tokens willy-nilly to people who aren't trusted or who didn't actually solve their CAPTCHA or didn't meet the bar. And I think Chris made this nice little hilarious Spider-Mans pointing at each other of essentially the failure modes here are origins are saying, I'm getting some bad traffic coming in that clearly shouldn't actually have passed the attestation checks. It says issuer, why are you giving me these bad tokens? He says, hey, the tester, you're not doing the right thing, and the attester could be like, oh, my checks are fine. How do you know that that's actually fraudulent? So we definitely need a way out of this. And this was Chris's suggestion for how to address this. In general, this should be a rather exceptional event, and essentially the ecosystem needs to come to some recognition of either give a way for origins to report back to the issuer that things are not working as they would expect. So I think we do need some extra text on this. I don't know, Chris, if you wanted to comment on what you were imagining here.
I didn't have anything specific in mind right now, because as you say, or as I sort of jotted down here, I do think that this will likely vary based on your particular deployment, whether or not it's like joint attester issuer, split attester issuer, and what the configuration is of the different parties. We might just note that if things go awry, signals start firing for reasons that they shouldn't start firing or whatever, that this is an exceptional event, and applications should deal with it some way. I don't have a very eloquent way of like stating that some way right now, but I'm hesitant to like prescribe anything specific.
Yeah, it eventually needs to be at the point where if some party like an attester or issuer starts doing bad things, they kind of need to be kicked out of who's trusted by the other parties. That the origins say, oh, I no longer trust this issuer, or the issuer says, I no longer trust this attester because I need to make sure that my origins keep trusting me. So essentially, the roles of running a token issuance service involves maintaining your credibility, and you need to make sure you have some way of getting feedback to make sure you're letting bad clients in.
Mm-hmm. And it's not like, I guess, if attestation fails once, that particular tester should indefinitely be untrusted. I can imagine scenarios where, like, I don't know, there's like a 0 day and like somehow for some reason like attestation is like subverted or whatever, compromised. But once that's patched, everything's back to normal. So, I mean, we can work on the text offline, I think, but I don't think the implication needs to be like permanent adjustments to the trust model. It's just like temporary workarounds or mitigations or something.
Right. Someone compromises your attester. If that's detected, they take themselves out of the pool until they can patch their 0 day, and then they come back in.
Yeah.
Cool. Right, and I think that's it. So those are essentially the main two open issues. We already have the IANA pull request out, so we just need to refine that based on what we have here, and then we want to add this architectural text. And beyond that, we think these basic ones are pretty good to go. So if there are other pieces of feedback on those, I'd like to hear it, or if the chairs have any comment around what they want to see. I think the last call is a good way to also initiate reviews. Sophia.
Yes, Sophia Celia from Brave. I was having two questions. The first one is, it seems like it's going to be a last call, or at least that's what is being asked of. Is this waiting also on the standardization or the last call, at least, of the documents that currently are sitting in the CFRG, like the BOPRF or the blinded RSA, that are currently kind of dependencies on the Privacypass main trust? And the second thing, the new current architecture of the Privacypass protocol was kind of introduced on the December of last year, and now there's an introduction of different issues and attesters and origins and how they can interact with each other. And there's different ways that they can either collude with each other, or, as you just mentioned in one of the issues, the different entities can be compromised. Has there been any interest of the working group to provide a more formal documents of any security/privacy analysis of the different kind of attacks and threat model that all of those entities colluding or interacting with each other can pose?
Cool. For the first one, maybe Chris will have opinions on the relationship with the CFRG documents. I think that's kind of up to the chairs of Privacypass and CFRG to how they want to coordinate that. I think those other specs are stable enough that it would be fine to run them in either order through that, but maybe ship them off to IASG or IRSG review around the same time. That's fine. And then regarding the other one, I think the document does try to talk a bit about how you do the analysis. If there are specific things you think the architecture should add for extra analysis, then we could add it. But I think it would also be perfectly fine to have further documents analyzing different aspects of this. I think in general, these split models that we have for Privacypass, we have for Oblivious HTTP, we have for using mask proxies, they all share some interesting properties. And I know there was even discussion in Perog about what are the terminologies we use for doing privacy analysis there. So this certainly should not be the last word on how we talk about this architecture and think about analyzing these deployments.
Yeah, Mr. Vat, a quick question about credibility of the entities that you mentioned. Can you say more about those? Like, is that going to be part of the solution? Or?
Which entities are we
Like
talking about?
the parties that involved in this, like you talked about credibility of those parties if they misbehave or something like this, right?
Right. So in the architecture, you have the entities that are redeeming tokens,
Right.
and they don't necessarily get to see all the information about the clients themselves. And so they have a trust dependency on the entity that issues tokens. And that entity's credibility comes from the fact that either they are doing their own attestation or checks, like maybe they had issued CAPTCHAs or they had done some verification, or they are working with one or more other services that can do that attestation of the clients. So essentially it is a transitive trust and credibility chain there. And it's essentially up, if an issuer is going to work with multiple forms of attestation, it needs to make sure that it is only using kind of good enough ones to meet the requirements of the origins that it's serving tokens to.
Okay.
That makes sense.
Thanks.
And Chris.
Yeah, just to respond to the CFRG thing, because you kind of called me out. I think both of the blind RSA and the VOPF documents are basically ready for research group last call in that group anyways. Now the process does take longer, unfortunately, in the IETF than it does in the IETF. So I guess it's up to the chairs, as you suggested, to figure out how they want to stack things and what the pipeline looks like. I don't think we need to block on, having gone through all of the process in CFRG to move things forward here. On the comment that was just raised at the mic regarding like parties behaving correctly, I mean, I think it's just sort of par for the course. Like we expect protocol participants to implement the protocol honestly, just like we expect TLS servers to implement that protocol correctly and not post keys to Twitter or whatever. And things break down when they don't behave correctly. And this is a little bit different in that we're trying to design against potentially malicious parties in the protocol. But for the most part, like the behavior as specified, we just sort of assume that they're following that specification. Yeah.
Cool. All right. I think we're probably out of time.
Okay. Thank you, Tommy. I guess I believe Chris Wood is presenting the next section.
Okay. All right. So this is an update on the rate-limited Privacypass issuance protocol that we presented last time. It's actually undergoing an adoption call right now. I kind of wanted to take a step back from the internal technical details of the protocol because it is admittedly somewhat complex. We tried to spend a lot of time as the editors of the document clarifying what the different functions of the protocol are, what the different steps are, and whatnot. So here I just want to kind of talk about the high-level motivation for the protocol, what the different properties are in terms of how much state it has, different pieces or different entities in the protocol, and what the desired or end resulting privacy properties are, as well as touch on some open issues. So having said that, as a recap, because it wasn't covered in the base protocol document, Privacypass is now, as a architecture, is composed of two sub-protocols, one of which is the redemption protocol. This is the protocol that's run between client and origin for the purposes of redeeming tokens, and it's based on well-established like HTTP authentication mechanisms. Origin will challenge the client to present a token, or may challenge the client to present a token with certain parameters in that challenge, and the client, if it can satisfy the challenge, presents a token in response with its retried request. Issuance is the complementary protocol, which effectively takes one of those token challenges from the origin and runs a protocol between the client, attester, and issuer for the purposes of producing a token that's bound to that particular token challenge. We've sort of arranged things such that all of the complexity in Privacypass is sort of encapsulated in the issuance protocol, because there's expected to be sort of like very few implementations of these, like one implementation of one client implementation that serves many clients and so on. Whereas we, on the flip side, on the redemption side, we wanted adoption to be incredibly easy. So for example, in the basic type 2 tokens that Tommy was referring to earlier, like consuming and verifying a token is as simple as verifying an RSA signature. It's really straightforward. Okay, I'm going to walk through sort of how these two things work in concert. So on the left, we have the redemption protocol, which, as stated before, the origin produces a public key and a challenge to the client, and the output of this, or in response to that challenge, the client produces a token. And the desired property here is that the origin learns nothing about the client beyond whether or not it was able to present a token that it satisfies the challenge. That just one bit. On the right-hand side, the issuance protocol is, again, takes its input, this public key and challenge, turns it into a token with this dance between client, attester, and issuer, which for the basic issuance protocol is just a blind signature protocol or a VOPRF protocol or whatever. And the desired property here is that the issuer learns nothing about the client, in particular that it cannot link successive requests from the clients together. They each appear as independent, unlinkable requests. Unfortunately, the basic issuance protocol does not provide an obvious way to do per client rate limiting. So say you had an origin that wanted to, to limit the number of times a particular client had access to a specific resource. It cannot do so because by definition, the only thing it learns from the token is whether or not the token was able to present a valid token. And the issuer, the only thing that the issuer learns is whether or not like token issuance succeeded. It learns nothing about, or there's no concept of state anywhere in in the issuance flow. This is problematic because there's a lot of interesting applications where rate limiting is quite useful, and we don't want to fall back to things like rate limiting based on shared context across clients, like IP addresses. You have meter paywalls where you might want to limit the number of times a particular client's able to access some content. You might want to dampen damage or activities that bots from a particular bot farm are doing, and so on. Rate limiting is used in many, many places. So the question we asked ourselves for this draft is, how do we add rate limiting support to Privacypass without compromising on the security and privacy properties that were discussed for the basic issuance protocol? And before talking about sort of the mechanism, just I want to give a quick reminder for how like rate limiting is commonly implemented in practice. It's typically done with some algorithm called a token bucket or a leaky bucket, depending on which textbook you read, where the token bucket or leaky bucket is driven by two independent processes. There's one process, which is like the person trying to access the particular resource that consumes tokens from this bucket, and they're only able to access the resource if there are tokens available to consume. The other process, the token replenish process, will put tokens back in the bucket at a sort of fixed recurring rate, and the rate at which you replenish tokens in the bucket determines the overall rate limit. And so the way these two things interact, the dynamics of the interaction between requesting and consuming tokens determines effectively how clients are rate limited. Internally, you can think of this being implemented using like a simple hash table. So when a token replenish event comes in, the token bucket will just identify the context associated with the rate limit, and then increment some counter associated with that particular context. So in this example, the context is an entry in a hash table. There's a previous count n associated with it, and just bumps up the count by t. T is the replenish count. Requesting a resource does exactly the same thing to identify the rate limiting context, and then go into the hash table. But now it just decrements, the counter associated with it, and if tokens are available, processes the request. If not, drops the request on the floor. Okay, so we wanted to implement basically this functionality under certain constraints. As I was saying before, we want to maintain the security and privacy properties that we originally had in the protocol. In particular, we don't want the origin to learn anything beyond a bit. And this bit in this case is not only was a client able to produce a token, but the client was able to produce a token without exceeding the rate limit. That is effectively the bit. Any other sort of state at the origin side could be potentially abused to track clients, and so we didn't even want to explore that avenue. We also wanted adoption to being as simple as it was for Privacypass. In fact, the tokens that are produced for the rate limiting version are indistinguishable from the tokens for the basic issuance protocol, both verified with the RSA signature. We wanted the issuance protocol, the thing that actually produces tokens and necessarily deals with the state aspect of rate limiting, to be as close to stateless as possible. Of course, it can't be stateless because then you can't be really rate limiting. Someone has to have state around like how many tokens were issued for a particular client origin pair. And the question is like, where is that state kept and how is it enforced and whatnot? But we want to minimize the state because we want to make it easier to actually operate an issuer and a tester. And importantly, for certain deployment models of Privacypass, we wanted to make sure that neither a tester nor issuer are able to link client origin pairs together. So right now, in the basic issuance protocol, there's no like information exposed to the issuer during issuance. But if we now consider rate limits applied on a per origin basis, intuitively someone has to see or enforce some state based on a specific client and a specific origin. But we did not want that state to reveal anything about a specific client going to a specific origin, like my laptop going to example.com or whatever. So we're aiming for something that's close to like OHTTP and ODO and sort of style, where one party sees like half of the equation. Okay, so functionally, what the issuance protocol does in this document is it extends the basic issuance protocol with a couple of new properties and features. The first of which is that the issuer that's actually producing a token necessarily learns the origin associated with a token challenge, because this is necessary because the rate limits that are sort of enforced in the system potentially differ on a per origin basis. So the issuer needs to learn which origin is this token request for, so I can pick the right limit and respond accordingly. Testers in this protocol have much more responsibility than they do in the basic issuance protocol. Beyond just relaying requests and responses back and forth between client and issuer, they now learn what we refer to as a stable mapping, or as sort of described earlier, the rate limiting context on a that is specific to a per client secret and a per origin secret. And that word secret is important because a tester doesn't learn like client A is going to example.com. It learns client A is going to random thing, and then client B is going to different random thing. And this state is necessary because this, in this particular design of the solution, we have the attester as the entity responsible for enforcing the rate limits on per client and per origin, on a per client and per origin basis, which we think is a reasonable trade-off given all things considered. And also differently from the basic issuance protocol, token requests can now fail, because if you try to issue a token or request a token, you've exceeded your rate limit, the attester will just drop your request on the floor, or as actually happens in the protocol, it returns an error to the client. Okay, so functionally, just sort of walk you through what the issuance protocol does at a very high level without describing any of the technical details internally. Those are best kept to the draft. This is just the issuance protocol. The redemption protocol remains the same. You'll notice on the left, as input to the client, there's some public keys, there's a challenge, there's some other things, specifically a secret key, SKC, that the client maintains for sort of its, for all of the rate limited requests that it has to, or that it wants to access through a particular tester, because that's the per client secret. But anyways, there's a request response flow between client attester and issuer. And what the attester does using this request response flow is basically compute the stable mapping or compute the rate limiting context, decrement the count associated with that rate limiting context, and then respond to the client with an error or with the token request accordingly. And there's a lot of like complexity or there's a lot of stuff that happens behind the scenes to actually do this this actual stable mapping computation, and do it in such a way that the attester can't like try to figure out what the client was after without the client's active participation. Mary, if it's okay, can I take questions at the end? If she's in the room, I can't hear her. Okay, thank you, Mary. As a result of this particular design, the way state is split across the various participants is as follows. So as before, the basic issuance protocol, the origin keeps sort of a constant amount of state. In particular, it just keeps the token associated with the token or the public key necessary to validate tokens. Clients maintain state that's on the order of the number of servers that they want to request. Testers now maintain the most amount of state on the order of the number of clients multiplied by the number of servers that all of those clients are accessing. And issuers only maintain state that's on the order of the number of servers that are actively configured for this particular issuer. There's, I guess, if you're looking at the privacy properties, as before, it's not possible for origin or tester to link any two requests together to the same client. So we'd sort of maintain parity with basic Privacypass here. But as I said, the tester does learn this sort of state, this rate limiting context based on a per client and per origin secret. A rationale for why this was reasonable is that the tester is already in sort of a privileged position with the client's IP address in the split tester issuer model. And as a result, it's sort of already trusted to handle this sensitive information and has less incentive to misbehave. Because if it wanted to just do bad things to the client, it could just forward the IP address onto the issuer. Okay, so I think there's two, there's one sort of fundamental open issue that's worth some analysis and consideration. The first of which is this sort of state that the attester learns is effectively equivalent to access patterns that clients might have in terms of like, browsing the web. And it's unclear how much leakage is actually possible or revealed through this access pattern. And in particular, if an attester could combine this information with certain auxiliary information for the purposes of, potentially learning what origin a specific client was after. There's another open issue that we think we have a technical solution for. We would have a better technical solution if we had a partially blind signature, but we do not yet have one. So we have a different solution to it. Details are in issue 218. As a status update, to assist with the adoption call, we have two interoperable implementations, one of which is the open source implementation that Tommy referred to earlier. You can test it out. It supports all the basic issuance protocols as well as the rate limiting one. And we do have security analysis that was done. It was submitted for peer review. Unfortunately, did not capture this issue just alluded on the previous page, but we're working right now to update the analysis to make sure it is taken into account and that our mitigation does actively prevent it. And we'll hopefully update the working group with that analysis when complete. Okay, that's it. Thank you for letting me run over. I'm sorry, Miria. I could take your question now. Jonathan.
Does this consider Sybil attacks, or are they considered out of scope here?
What would be the Sybil attack in this case?
So I'm a client and I want to overwhelm an origin, so I just say to the attester, oh, I'm a new client now, give me a new bucket. I have now 15 buckets and I can do much more traffic.
Yeah, so one of the assumptions is that the attestation that's done between client and attester prevents that from happening. So you can't just like endlessly spin up new identities as a malicious client and do that sort of Sybil attack. Of course, if like your attestation does not ensure that that happens, then there's an obvious problem with this. So with the protocol assumes that the client attester relationship enforces or prevents that from happening. So for example, go ahead.
By IP address, or?
Could be by IP address. It could be based on like device attestation. So you would have to have distinct devices in order to do this. It depends on what type of attestation is done between the client and the attester.
Thank you.
Yep.
Mia Kulin, yeah, thanks for the overview. I have a question about, so in the architecture you propose, the rate limit is provided from the issuer to the attester. And
Yeah.
The other option would be to actually provide the count from the attester to the issuer, and then the issuer could drop the packet. Did you consider that?
Yeah, actually, that was how the draft was previously written. We had basically the attester send the count to the issuer, but we determined that that leaks too much information. In particular, based on the counts that the issuer sees, it could figure out whether or not two requests for the same client or not. So as a simple example, imagine that the issuer just saw like n requests in a row in sequence, and every single time the count kept going up. It would just conclude that these are obviously from the same client.
Yeah, I mean, yeah. So you're also leaking a little bit of information because you provide the origin count, and when it's always the same. I mean, it's probably always the same for many origins or whatever. But like, there is a lot of like, yeah, it's a little trade-off. Okay. Yeah. Yeah,
that was the crux of the trade-off. Nick.
Nick Doty, CDT. I apologize if I'm repeating this question, but have we established evidence from people doing this sort of account creation or something like that, that this metering will be effective? I can see how this is effective for the New York Times paywall, and if you want to come up with a complicated scheme to do that, maybe that's fine. But I sort of get the impression that if you're in the abuse case, there's not going to be a single threshold where sort of yes, no is useful, but you might want to know the number because you could escalate or something. That it's not always going to be like good or bad in those abuse cases, but that they would want to just use that as a signal. So do we have a sense from those use cases that a single threshold is going to be helpful?
I think this is still something that's under discussion in the anti-fraud community group. There's a lot of uncertainty with respect to, what are the useful signals that can feed into some anti-abuse system, and what role like different types of attestation and rate limiting plays in those scenarios. So I hope the conversation and an answer to your question evolves in that group, which is where sort of the practitioners are iterating on, what is the value of this as a application specific thing. But I don't have an immediate answer for you because that group, you may be, you're actively participating in it. It has many conflicting opinions from different people. So we'll see how things go.
Okay, I'll make sure I continue that there. Thanks.
Yeah, to chime in as just like another author, we have, obviously we can't know how everything will play out, but when we have discussed with various anti-fraud systems that would be interested in using Privacypass in general, essentially like there's a spectrum from like the basic Privacypass that has no rate limit guarantees at all other than client implementation, and like what they would have today with actually, like here is your IP and here's your cookie and I can like track you, and like this falls somewhere in the middle. So like there are clients or origins for whom this will improve their ability to use this as a meaningful fraud signal. It will not allow them to do all of the things that they could do if they got an exact count per client and re-identified someone, but it increases the number of sites that can use Privacypass meaningfully today, and we'll see if we need to go further than that. But this is a useful jump.
Yeah, I sort of view it as another tool for them to use, a tool that discourages use of like existing tools that might have like a bad privacy posture with respect to the client, like tracking based on the IP address, for example.
Thanks for that discussion. Yeah, just reminding the group, this document is subject to an open adoption call that will end in about 2 weeks. So please do comment on the mailing list and share with the group your opinion of whether this document is suitable for adoption. And now we're on to our final section.
Okay, thank you. So this is just a reminder of a draft that a couple of us had written on the side after realizing that there's this common problem that's emerging in many different application areas inside the IETF, OI, Privacypass, in particular, on in an attempt to distill like all the different ways that people deal with key consistency and discovery in practice, and that's the intent, that's the motivation. So this is not like a tremendously new update to that document, but just a reminder, and hopefully at the end we'll talk about like what we can do with this if we want to do anything with it. Okay, so as I said, there's a number of protocols in the IETF right now that actually depend on clients having some consistent view of their keys, so that they don't, when actually using these systems, they don't reveal information that they shouldn't reveal to a malicious service provider. Privacypass is one particular case where you want the issuer verification key to be consistent across all clients that are interacting with that issuer. OHTTP is another one where you want the gateway's public encryption key to be consistent, and it's like configuration, the URL, and all those things. I highlighted that information, but it's there. Tor is another example where you want relay public keys to be consistent across all clients. And fundamentally, there's like two common requirements for these different types of systems, which I'll call unlinkability and authenticity. Unlinkability is informally that servers can't link usage of a specific key to an individual user, and then authenticity is that when clients are using a key, it's a key that was intended for that specific server. It's not like a key that someone else owns that is not the intended server. So why is this important? Imagine you had like a scenario where there's a bunch of clients interacting with some server. The server makes its key K available to those clients, and the server uses that key. The client uses that key. A client uses that key, produces a function based on the key, and sends the output of the function to the server. The server assuming all clients have a consistent view of this key, the only thing it learns is that this was sent from one of these n clients in this particular set. If, however, the server managed to distribute the key in this particular way, where one specific client has a key K1 and all other clients have a different key, usage of a key might reveal what the specific client was that interacted with the service, which is not great from a privacy perspective and something we'd like to avoid. So consistency here means that all clients, again, have the same shared view of the key for the particular server. There's also authenticity, the other informal principle. So imagine you had now an adversary that sits between the server and the clients, where the server makes its key available, its authentic key available, but then the adversary, slips in its own malicious key K prime and gives that to the clients. Clients, if they don't know any better, any function computed based on this particular key K prime reveals something that was originally intended for S. So in the case of like OHTTP, that might be an encapsulated request encrypted to someone that is not the actual gateway, but it's someone else, which would not be great. So we also want to avoid this. And sort of simplifying things a lot, basically what the draft advocates for is that these two properties on linkability and authenticity mean that every single client has a consistent view of the server's intended key, and then that view is correct. And systems that actually enforce these two things we call key consistency and correctness systems. And the design space for this sort of thing is huge. I mean, there was a discussion based on key consistency in OHI earlier in the week, based on one of Ben's drafts, and that touched on one solution in this design space. There are other solutions that have different complexity in terms of operation, trust model, and so on. So the actual system that's used to enforce consistency and correctness can vary based on all these external factors, or based on all these factors, some of them external, I guess. Roughly speaking, the design space kind of boils down to these four things. First of which is fetching a key through a trusted proxy. So clients that belong to the same anonymity set would ask a trusted proxy, hey, give me the key, the consistent and correct key for this particular service that I'm using in the server, and the proxy is trusted to present the correct key. You could fetch and verify through a trusted proxy, which is what the double check thing or double check spec roughly does. You could fetch through multiple untrusted proxies or less trusted proxies and verify that you get back the same answer. Or you could sort of stick all these keys on a bulletin board and audit that bulletin board and make sure that you're getting the latest contents of the audited bulletin board. Where a bulletin board here is just an authentic append-only log or something like that. And these approaches, I'm going to walk through them in pictures just to really drive the point home. These are pictures of these different solutions. Again, they have different applicability based on your application configuration, your deployment model, your threat model, and trust model, and whatnot. And so there's no one size fits all or correct solution here. It's a pile of trade-offs. So in the trusted proxy case, as I was saying, there's a proxy in the middle that gets a key and then vends it out that same copy to all clients. Pretty straightforward. In the multi-proxy case, where clients might go through different untrusted proxies to ask the server to present its view of the key, clients could check to see whether or not a server is trying to lie and change keys, in a malicious attempt to tag clients. I have here listed that consistency double check is sort of an example of this. Slightly different, but I'm kind of they're close enough in spirit that I just kind of threw it on here. And then there's the bulletin board external database, which stores the keys, and then clients just pull it down. And there's some assumption that there's an ecosystem built around this bulletin board for verifying that everything is correct and consistent. Like Connex and key transparency were basically an instantiation of this concept. Okay, so consistency has come up time and time again, in particular this week, and I think we're really going to have to address it with Ben's draft. The question is, whether or not there's value in this complementary document that sort of describes the rest of the design space, or some other pieces of the design space may not be exhaustive. there is no specific section in the Privacypass charter that to sort of address the key consistency or key tagging issue. So after discussion with the chairs, we basically are proposing to bring this document as informational as a working group, like supporting document or something to be published. I don't think it matters that much, to sort of help inform the discussion around consistency double check or other solutions as they emerge. And that's our proposal. Curious to hear what folks think. Yeah, Tommy.
Yeah, thanks for doing this. This is clearly very important. I have no idea what working group this belongs in. I don't think it matters too much. We don't have one to do it in, but we should do this. The one comment I had is, if I wonder if the approach of double check, not the specific protocol instantiation, but the approach of it could be mentioned more explicitly here. It kind of seems like implicit when you're talking about, oh, you have proxies you can go through and you can go direct, and like maybe laying that out and bring some of the double check in, because it feels like different protocols like OHI, if there is a way to do a specific OHI key config lookup that can adopt double check, but other things, even if they don't fit into one particular config bag, like different key configuration locations could use double check and use these different techniques. So we could talk about techniques here and then just let other protocols say, oh yeah, and then you use that technique or that technique or that technique.
That sounds like a reasonable approach. And certainly we didn't mean to like intentionally omit double check variant. It is, as you say, it is a slightly different technique than the multi-proxy discovery. I like vastly oversimplified things on this particular slide. So we could add a section there. Alternatively, depending on like Ben's preference here, we could like just take all this content and like put it in an appendix in his draft as like, here are alternative solutions that if you didn't want to use double check or whatever. I don't think it matters that much. Although to Tommy's point, it does seem like it might be useful to have a place to somewhere to point and say, this is the consistency mechanism I'm using in a specific deployment or in my specific protocol.
So the authors of this draft have requested an adoption call for this draft in the Privacypass working group. I don't believe such an adoption call has been made yet, but the chairs will consider that. And if an adoption call is started, you'll see the announcement on the list. So please do review the draft so that you're prepared in case such an announcement appears. We are over time and we've completed our agenda. Thank you everyone for participating and making this a great Privacypass session.